Hello and welcome to Shridevi Classes YouTube channel where we inculcate interest and confidence in engineering education. Today in our playlist Induction Motor, we will study NEMA design classification of squirrel cage induction motor as Class A, Class B, Class C and Class D, and we will understand how rotor core lamination or rotor winding decide starting and running performance of an induction motor, and according to that NEMA has classified four type of induction motor as Class A, B, C and D. Let's start. National Electric Manufacturing Association of United States of America has done significant work in design, development and standardization of several electric equipments, and their work for three-phase squirrel cage induction motor is also very significant. NEMA has classified squirrel cage induction motor in four different design codes, and they are called Class A, Class B, Class C and Class D. Now this NEMA motor design classification is according to locked rotor condition, that is called starting of induction motor, what amount of torque it is producing, how much amount of current it is drawing at the time of starting, what is the maximum torque capability of induction motor, that's called breakdown torque, and for full load conditions, for normal running conditions, what is the speed or slip of induction motor. That parameter of starting and running performance decide the selection of motor, and to help application engineer, NEMA has classified motor in four categories, and this behavior of starting and running performance is based on design of rotor core lamination or rotor winding, and how this constructional feature makes functional impact on squirrel cage induction motor performance, and that is used to select a particular motor for a particular load applications. So to understand that, let's first understand different significant starting performance parameter and running performance parameter one by one. For a squirrel cage induction motor, starting torque is also known as locked rotor torque, and it is that torque or rotating effort which is generated by rotor when it is stationary, and rated starting torque is that torque which is produced by rotor of squirrel cage induction motor when rated voltage and rated frequency supply is given to stator side. We usually refer starting torque as a ratio of full load torque, and full load torque is that rotating torque effort produced by induction motor which match load requirement, and motor can continuously run at that load torque conditions safely without exceeding its normal temperature rise conditions. For a typical standard NEMA B design motor, the starting torque is 1.5 times of full load torque, or it is 150% of full load torque when stator is given rated voltage and rated frequency. If a star delta starter is used to reduce line current to 1/3, the same starting torque will become 1/3, and for a standard NEMA B design or standard NEMA A design motor, this torque will become only 50% of full load torque. Now a motor with starting torque take a little time to accelerate and attain full load speed conditions very near to synchronous speed, and it took around half a minute, 30 seconds to 2-minute duration. And if it is lightly loaded and inertia of load is insignificant or small, then it would take 10 to 30 seconds to accelerate and attain full load speed conditions. But if the same motor is heavily loaded, it would not only take high amount of time to accelerate, at the same time we need a higher amount of starting torque to accelerate such motors. But normally the standard designed NEMA A and NEMA B type induction motors are used with fan and pumps, where torque on motor develop only when motor get speed up, or at start positions load torque is insignificant, and a small amount of torque produced by such motor can accelerate our motor in routine manner. At the time of start, motor produce a starting torque, and a connected load also demand a certain amount of load torque, and the difference of motoring torque and load torque is act as a accelerating torque, and due to that accelerating torque, motor start acceleration and attain speed. Due to complex dynamic behavior, as motor attain speed, its starting current sharply decrease in magnitude, and at certain low speed operation condition condition, motoring torque initially decrease to a lowest value up to point B, where accelerating torque become minimum. But after that, motoring torque sharply and gradually increases, and accelerating torque also accelerate and increase speed of rotor rotation, and at certain speed or slip conditions, motor attain maximum torque, and that maximum torque is known as breakdown torque or pull-out torque. Now this breakdown torque will occur at a particular slip condition where rotor per phase leakage reactance become equal to rotor per phase resistance. So the speed or slip at which breakdown or maximum torque occur depend upon rotor leakage reactance and rotor per phase resistance. Now the magnitude of breakdown torque is an inverse function of standstill rotor leakage reactance, and for smaller value of leakage reactance, breakdown torque would be higher. For a standard NEMA B design motor, breakdown torque is approximately 2 times of full load torque, that is 200% of full load torque, and after that the further acceleration or increase of speed start decreasing motoring torque. And in this negative torque speed characteristic region at certain position, the load torque requirement and motoring torque intersect each other, and motor will continuously operate at that intersection position, and that position is known as full load torque, and that slip corresponding to full load condition is known as full load slip. Before attaining full load conditions, if anywhere load torque demand is greater than motoring torque, then in that case motor will rapidly deaccelerate and abruptly slow down and stall. So we have to ensure that during starting operation, the motoring torque produced by motor must be greater than the load torque requirement. For a typical NEMA design B motor, the starting torque at rated voltage and rated frequency is 150% of full load torque, and if the same motor is started with a reduced voltage star delta starter, in that case the starting torque will become 1/3 or only 50% of full load torque. And if a motor got a heavy load start and that heavy load requirement is more than the starting torque produced by a motor, then in that case motor will not start and remain stall it as it is, and such operation for a small duration drawing enormous high stall condition current may damage motor winding. So one has to ensure for smooth acceleration and start, the motoring torque must be more than the load torque requirement. As motor and load both accelerate at certain specified speed or slip condition, motor attain maximum torque capability known as breakdown torque or pull-out torque position, and after that motoring torque will gradually and sharply decreases as speed increases or slip decreases, and at the same time the load torque requirement gradually increases as motor attain higher and higher speed, and at one particular speed position the decreasing motoring torque and increasing load torque intersect each other, and acceleration of motor stops there, and motor now continuously operate at this particular speed conditions with rated voltage and rated frequency applied to motor stator, and rated load is connected to motor shaft. Now this load positions of steady state speed conditions or fixed slip condition is known as full load condition, and in this full load condition motor will run continuously in controlled temperature conditions without damaging any of its functional component, and many a times this full load conditions is also the most optimum performance condition of motor. At this load condition motor have maximum efficiency as well as the best operating power factor conditions. Now the speed or slip at which this full load torque exists is known as full load speed or full load slip, and for a typical NEMA class B design motor the full load slip is around 2%. That means rotor speed and rotating magnetic field of motor have a speed difference of only 2% of synchronous speed for 50 Hz supply and 4-pole machine. When the synchronous speed is 1500 rpm, the full load speed with 2% slip is 1470 rpm, so the difference is only 30 rpm. For a standard NEMA B design motor, the maximum torque developed by motor is 2 times of full load torque, so that if all of a sudden the motor torque requirement increases and even become about double, the motor will operate in this stable region, and if accidentally the load torque requirement exceed 200% limit, and in that case the motor will stall as load torque is much more than what the torque motor can produce, and deceleration further reduce motoring torque capabilities, and in that case motor will ultimately stall, and some overload protection of motor for safety of motor must disconnect supply from motor to safeguard motor winding, otherwise motor may also damage itself. For a squirrel cage induction motor, starting current is also referred as locked rotor current, and it is measured from stator supply line at rated voltage and rated frequency supply when rotor is at rest position and motor is standstill. Now at standstill condition, the squirrel cage induction motor behave like a equivalent transformer with secondary short circuited and primary, that is stator side, draw relatively large amount of current. Now as motor accelerates by starting torque and attain speed, this starting current sharply decreases, and when motor attain full load conditions at rated voltage and rated frequency supply and required amount of load on motor rotor, then the current decreases to a steady full load current condition. And for a standard NEMA B design motor, starting current is 640% of full load current, whereas for NEMA A design motor, this starting current is 8 to 10 times of full load current. Now such high starting current produce considerable amount of line voltage drop and affect the performance of all other electric equipment connected to same supply system by reducing their voltages. So one has to limit or adopt suitable starters to reduce the inrush of starting current. Now depending upon connected load inertia, a squirrel cage induction motor may take 30 seconds to 120 seconds to attain full load speeds, and after that the current becomes stable and reduced to full load current conditions. We have explained several performance parameters of squirrel cage induction motor at the time of starting and at the time of running. We have explained what amount of torque a standstill rotor produce when rated voltage and rated frequency supply is given to stator, and that torque is called as starting torque. And during starting, a motor draw relatively high amount of current. That current is known as starting current. Now after acceleration at a certain speed position, motor attain maximum torque capability, and that maximum torque capability is known as breakdown torque. And after that, as speed increases, motoring torque decreases and load torque increases, and at one particular torque position the two will intersect, and that steady state position is known as full load condition. At this full load condition, motor can continuously run without excessive temperature rise in safe conditions, and the torque amount of this particular operating condition is known as full load torque. The corresponding current is known as full load current, and the slip at which this stable condition exists is known as full load slip. And for a standard NEMA B design motor, starting torque is 150% of full load torque, starting current is 640% of full load current, and maximum torque or breakdown torque is 200% of full load torque, and full load slip is 2%. For other requirement, NEMA has specified class A, class C and class D type of motor. Let's understand how NEMA classification works. National Electric Manufacturing Association NEMA of United States of America has made classification of squirrel cage induction motor in 4 classes as class A, class B, class C and class D, and this classification of NEMA is based on design of laminations used for rotor core. Now these laminations may be on shallow depth near periphery or may have a deep depth well inside the rotor core, and this depth of rotor conductor in core decide amount of flux linkages, and a deeper bar conductor have higher amount of leakage flux, higher amount of leakage reactance, whereas such narrow slots near periphery have small amount of leakage flux and leakage reactance, and this leakage reactance decide the maximum torque capability of motor, the slip of maximum torque and the operating power factor of our induction motor. Similarly, rotor may have a smaller cross section of conductor bars or have a large cross section area of conductor bars. Higher the cross section area, lower would be per phase rotor resistance, and smaller rotor resistance will produce smaller amount of starting torque, smaller amount of running slip, and better efficiency. So the rotor design decide the performance of motor at the time of starting as well as at operating condition, and how that works in these four class A, class B, class C and class D type of motors. Let's explain that in detail. The first standard motor of NEMA, National Electric Manufacturing Association, is called as design class A type of motor. Now these motors are designed for better running performance and for higher efficiency of operation. Now in these motors, the rotor core laminations are selected in such a way that rotor bars are quite large in cross section, but they have smaller depth, and that too near the surface of rotor. Now due to smaller depth, the rotor conductor would have smaller amount of leakage flux and smaller amount of leakage reactance, and since rotor got a high amount of cross section area available for rotor bars, so it have smaller amount of per phase rotor resistance. So these rotors are designed with smaller values of both per phase rotor resistance and per phase rotor leakage reactance. Since both rotor resistance and reactance is small, so at the time of starting, such NEMA design class A motor take considerable amount of starting current, that is 8 to 10 times of full load current, but due to small per phase rotor resistance, the starting torque produced by such motor is relatively small, as starting torque is directly proportional to per phase rotor resistance. But due to small rotor resistance, the motor have small amount of copper losses and higher operating speed or lower slip of full load conditions. So due to that low slip operations, motor have higher efficiency. So their starting performance is not good, starting current is high and starting torque is low, but their running performance is good. Now these motors have smaller depth of conductor bars, have lower amount of leakage flux or leakage reactance, and since the maximum torque produced by a motor is an inverse function of leakage reactance, and these motors have small amount of leakage reactance, so they have breakdown torque or pull out torque is good. NEMA design class A was the first standard motor design for good operating conditions and higher efficiency operations. Now in these motors, both per phase rotor resistance and rotor leakage reactance is small. So at the time of starting, it take considerable amount of starting current, and its starting current is 8 to 10 times of full load current. Now even with that high amount of starting current, since rotor has small amount of resistance, so its starting torque is only 150% of full load torque, so they won't have a high amount of starting torque and have considerable amount of starting current, so their starting performance is not good. But since these motor have small amount of rotor leakage reactance, so they produce considerable amount of breakdown torque, and their maximum torque capacity is 250% of full load torque value. They also have a very good running operations due to small amount of rotor resistance, and their maximum torque will occur only at a slip value of 5%, and full load conditions will occur at a slip of only 2%. So due to small value of operating slip at load conditions, they have small amount of rotor copper losses and very good high efficiencies. But since their starting torque capabilities is small and starting current requirement is high, so they are used only with those loads where starting torque requirement is relatively low, such as fan, pumps, blowers, centrifugal pumps or compressors or motor generator sets. And usually to reduce high amount of starting current, we use a reduced voltage starting, either star delta starter or soft starter, so that in rush of high starting current won't make trouble of line voltage drop to other electric equipment connected to same supply line. For standard economic high efficiency operating conditions, NEMA has designed class B type of motor, and these class B type of motor is an improvement over standard class A type of motors. In class A motors, we have broader slot of smaller depth but considerable cross section area near periphery, whereas in class B type of rotors, we have a deep slot with considerable amount of cross section area and considerable amount of depth in rotor core. Now this improvement of rotor structure has optimized the starting performance of motor, and now a class B motor have both running and starting performance optimized, whereas in class A motor running performance are very good, but starting performance is not that good. Like class A motor, class B motor also got small amount of rotor resistance, as rotor bar has considerable amount of cross section area. So both motor are designed with small amount of rotor resistance. But in class B motor, since rotor got a considerable deep depth of rotor bar, so lower part of rotor has considerable amount of leakage flux and leakage reactance. Now at the time of start in these class B motors, when rotor have induced EMF of supply frequency, the lower part of deep rotor bar have considerable amount of leakage reactance and impedance. So current got unequal distribution in this deep bar of rotor, and due to non-uniform distribution of current in rotor bar, the effective rotor resistance get increased, and that increased resistance and increased reactance of rotor has reduced starting current of motor, which was 8 to 10 times of full load current in type A motor. Now for type B standard NEMA design motor, this is only 6.4 times of full load current, and since rotor got higher amount of effective resistance due to uneven distribution of current at the time of starting, with that small starting current 6.4 times of full load current, it produces the same amount of torque as it is produced by 8 to 10 times current in type A motor. And this motor, type B standard NEMA design motor, produce the required 150% of full load torque at the time of start with 6.4 times full load current when rated voltage and rated frequency supply is given to stator. Now at the time of normal running conditions, when rotor induced EMF got very small amount of frequency, deep bar rotor leakage reactance become ineffective and current got uniform distribution in this large cross section area. So this rotor behave like a small resistance rotor. So it produce maximum torque at small value of slip, that is 5%. Type B motor got higher amount of leakage reactance, so its maximum torque capability is just 200% of full load torque, whereas in type A motor it was 250% of full load torque. So in comparison to type A motor, type B motor produce smaller amount of maximum torque, but both produce maximum torque at the same slip condition, and both have almost same full load operating slip, that is 2%. Rotor copper losses are also small and motor have very good efficiency. So it's both running and starting performance is optimized. After 1993, when energy prices has increased and drive the demand for higher efficiency electric motor has emerged, NEMA has improved standard class B motor and redesigned higher efficiency squirrel cage induction motor. And these higher efficiency induction motors are physically longer and heavier. They have higher amount of diameter and length so as to reduce specific electric and magnetic loading for same amount of power output. And these energy efficient motor require higher amount of active material, winding conductor material and core iron material. So they are a bit expensive, but in comparison to a standard class B motor which got efficiency of the order of 85 to 88%, these high energy efficient motors have efficiency of the order of 90%. New energy efficient motor got 2% extra energy margin. NEMA design class C motor is basically a double cage squirrel cage induction motor where we have a smaller cage near periphery and a deeper larger cage to the inner side of core. Now at the time of start, when rotor induced EMF got high frequencies, the current largely distribute in outer cage which has smaller cross section area and larger resistance. So starting torque, which is proportional to rotor resistance, become more, and at the same time increased impedance of rotor winding reduce starting current. So this double cage rotor with a dominance of outer smaller cage at the time of starting produce better starting performance. Now during normal running conditions, when rotor induced EMF frequency become negligible small, the effect of higher leakage flux or leakage reactance at deeper position in inner winding become insignificant, and current will distribute in an uniform manner since inner cage got higher cross section area, smaller amount of resistance. So this cage behave like a squirrel cage rotor of smaller resistance that results in lower value of slip, lower value of rotor copper losses and higher efficiency. So this double cage rotor behave like a rotor of high resistance at the time of starting and improve starting performance, and at normal running condition the same rotor become a rotor of lower resistance and increase efficiency. Now these class C type of NEMA design motor can be used for those load applications which require high starting torque, such as loaded pump, positive displacement pumps, reciprocating pumps, loaded conveyor, compressors used in air conditioning or refrigeration, crushers, textile looms, shearing machines, agitators. But compared to standard NEMA B design, these double case motor of class C design are little bit costly. So for normal duty applications, we prefer NEMA design class B motors, and for heavy starting torque loads, we use this double case NEMA design class C type of motors. Class D type of NEMA machines are altogether different squirrel cage induction motor. They have a small cross section rotor conductor winding near periphery of rotor. Smaller cross section results in higher rotor resistance per phase, and conductor position near periphery reduce amount of leakage flux and leakage reactance. So they also have small amount of leakage reactance. Due to small amount of leakage reactance, the maximum torque produced by these motors are higher than other motors, and due to higher value of rotor resistance per phase, their starting torque is also highest among all type of motors. So these class D design motors are used where we need extremely high inertia start, like loads of crane, hoist, and there are some applications where high peak loads occur all of sudden, and in these motors we connect load with or without flywheels, and in such applications of punch presses, shears, elevators, excavators, winches, pumping sets used in oil wells, and wire drawing machines, we use NEMA design class D type of motors. Let's compare all four designs together with torque speed characteristic of these class A, class B, class C and class D motors. NEMA design A motor got lower amount of rotor resistance per phase and rotor leakage reactance per phase, as they have wide larger slots near periphery without much depth. So their starting torque is 1.5 times of full load torque, but they draw a very high amount of starting current, which is 8 to 10 times of normal full load current. Due to small amount of leakage reactance, their maximum torque capability, breakdown torque or pull out torque, is 3 times of full load torque. But this motor got good running performance and full load slip is around 3%. Now standard NEMA design B motor is an improvement on class A motor, and they have deep case rotor. Due to deep case rotor, at the time of starting current become just 6.4 times of full load current, and it can produce starting torque 1.5 times of full load torque. Now it got a little higher leakage reactance, so its maximum torque capability is just 2 times of full load torque, and again running performance is very good, and full load slip is just 2 to 3% and have very good high running efficiencies. Whereas NEMA design C is a double case motor which produce very good starting torque, 2.5 times of full load torque with reduced starting current, and it also possess good running performance and high efficiency. Now NEMA design D got small amount of resistance, so it produce very good starting torque. Small amount of leakage reactance also ensure a high amount of maximum torque, so it can be used for heavy duty starting applications. To select a particular motor design for a given mechanical load, the torque speed characteristic of motor and that of load are compared, and a proper matching is made to select a proper design motor for a particular load. Now manufacturer of motors will provide information about how much is starting torque as compared to full load torque, how much is starting current as compared to full load current, what is ratio of maximum breakdown torque and full load torque, and with these informations one can select whether the motor supplied by manufacturer is suitable for our load requirement. The starting torque of a motor must be larger than the load requirement of motor at the time of starting. If it is a normal fan or pump type of application where load on motor occur only when motor gets speed up, so there is no need of very good high starting torque, and standard NEMA B design ensure 1.5 times starting torque with rated voltage, and if you take star delta starter and starting torque become 1/3 of normal voltage starting, then in that case starting torque is 50% of full load torque, and motor with that 50% of full load torque can accelerate and attain stable characteristic region. But if load is a heavy duty start type of load, then we have to use either class C or class D type of motor so as to ensure safe and smooth starting. Now at the time of starting, we also have to consider the starting current drawn by the motor, and NEMA standard B design motors are designed in such a way that with normal voltage starting they draw 6.4 times full load current, and with reduced voltage starting such as star delta starter, when the line current become 1/3 of normal full voltage starting current, that current becomes just 2 times of full load current. And with double line current, when a motor is started, it won't create much trouble to other appliances connected to the same supply by voltage drop problem. Now the maximum torque capability or breakdown torque capability is also very significant, as in certain load conditions all of a sudden the mechanical load requirement on motor may get increased, and normal NEMA B design have breakdown torque 2 times of full load torque. So if accidentally torque requirement on motor get doubled, even in that condition motor will remain in starting position. But if torque exceed beyond 2 times or supply voltage has reduced and torque has increased simultaneously, then in that case if pull out torque become less than the load torque requirement, then in that case motor has to deaccelerate and it will all of a sudden stall, and this is a dangerous position and a trouble to our manufacturing setup. So if there is a chance of sudden increase in motor load conditions, then we have to select a motor of higher breakdown torque, either NEMA design A motor or NEMA design C motor. We hope with this informative learning video you can understand what is significant of starting torque, starting current, breakdown torque and full load slip in motor operation and matching of motor and load conditions. Now you also understand what's the difference of rotor laminations in class A, class B, class C and class D motors, and rotor core laminations influence torque speed characteristic in all those 4 classes of coil cage motors, and we can select appropriate motor as per our load requirement. If you found this learning video useful, do share it with your friends, and for study notes and online classes, do join membership of Shridevi Classes YouTube channel. Happy learning. Thank you very much.